Sometimes we have a problem that's so complicated we wish there was a natural log or a log so that we could apply those log properties to differentiate first. Here's an example. To attack this problem straightforward, we'd write it as some powers here and then apply the quotient rule with the generalized power rule. But another trick that we could do would be to just ourselves decide to take the natural log of both sides of this equation. So we go from having an explicit equation for y to having an implicit equation for y. But the advantage we get is now we have a natural log on this side. Now, so the first thing we can do, this cube root is a 1/3 power, so we could bring that down in front. And we have 1/3 the natural log of x plus 4 over the square root of x minus 5. Now we have the natural log of a quotient, so we could rewrite this as 1/3 times the natural log of x plus 4 minus the natural log of x minus 5 to the 1/2 power. Of course, that 1/2 could come down in front by the power rule for logs, so we have 1/3 of the natural log of x plus 4 minus 1/2 of the natural log of x minus 5. So this 1/3 is multiplying everything because it came down before we split it up, but the 1/2 only belongs to the part that's the natural log of x minus 5. Okay, looking at this now, taking the derivative is going to be much easier. Just remember it's an implicit function though. We've got the natural log of y on this side. So if we take the derivative with respect to x of both sides, the derivative of the natural log of y would be the derivative of the inside over the inside. The derivative with respect to x on this side, we've got that constant 1/3 that comes through. The derivative of the natural log of the function is the derivative of the inside over the inside. And we've got this constant 1/2 here, and the derivative of this natural log is the derivative of the inside over the inside. So the derivative was actually pretty easy once we used these properties of natural logs to simplify. We're not quite done because we want to find dy dx. Right now we have dy dx over y. So I'm going to cure that problem by multiplying both sides by y. When I do, I get dy dx alone on the left, and I have 1/3 of 1 over x plus 4 minus 1/2 times 1 over x minus 5 times y, but y, of course, is this big ugly thing, the cube root of x plus 4 over the square root of x minus 5. So we've got the derivative now explicitly again. Dy dx is this particular function. We could, if we wanted to, combine these into a single fraction by getting a common denominator, and then we'd have something that had powers of x plus 4 and powers of x minus 5 times something else that involves x plus 4 and x minus 5, and we could cancel a little bit to simplify this answer. So maybe I'll just walk through how that would go so you can see. We have 1/3. If I get a common denominator here, this one would need to be multiplied top and bottom by 2 times x minus 5. And this would need to be multiplied top and bottom by x plus 4. So we get minus x plus 4 all over that common denominator. X plus 4 times 2 times x minus 5. Now this top term, the cube root of this quotient is the quotient of the cube root. So the top is x plus 4 to the 1/3. And the bottom is the cube root of the square root. So it's an exponent of 1/2 times an exponent of 1/3. 1/2 of 1/3 is 1/6. So we have x minus 5 to the 1/6. Keep going here. We have 1/3. This fraction simplifies a little bit because it's 2x minus 10 minus x minus 4. So 2x minus x would be x, minus 10 minus 4 would be minus 14, all over 2 times x plus 4 times x minus 5, all times x plus 4 to the 1/3, and x minus 5 to the 1/6. So all together now, we have this x plus 4 to the 1/3, and that's going to wipe out, let's see, 1/3 minus 1 would be negative 2/3, so we're going to have x plus 4 to the 2/3 downstairs. let's see, and 1/3 of 2, that's going to make a 6, isn't it? So we have upstairs an x minus 14, and 1/3 times 2 would make a 6 here. We have x plus 4 to the 2/3. Basically, with x plus 4 to the 1, but this 1/3 upstairs wiped that out. We have x minus 5 to the 1, that's 6/6, plus another 6 would make x minus 5 to the 7/6. So now we've got it as these various products. It might look a little bit simpler to us. Okay. Now in this problem, it was completely optional to decide to take the natural log. We could have gone through it just by using the generalized power rule and the quotient rule several times. We could have worked our way through it. We would have gotten down to the same answer by the time we put everything together. It was just easier to take the natural log. Sometimes, though, it's pretty much essential to take the natural log. In this example, I want to find dy dx, but this function doesn't fit either pattern that I know of. It's not a power because the power is not constant, but it's not an exponential either because the base is not constant. But if I take the natural log of both sides, then I can find the derivative because I can use the power rule. So once I have the natural log in the problem, then the power can come down in front, and it turns this into from some exponential that I couldn't deal with to some product that I can deal with. Let's go ahead and take the derivative of both sides with respect to x now. If you take the derivative of the left-hand side with respect to x, you get the derivative of the inside over the inside. To take the derivative of this is a product of two functions. So you take the derivative of the first times the second plus the first times the derivative of the second. The derivative of the first would be cosine times the second plus the first, which is sine, times the derivative of the second. The derivative of the natural log of x is 1 over x. If I multiply both sides by y, I get cosine x ln x plus sine x over x times y, but y is x to the sine x. So I find that dy dx is equal to cosine x ln x, x to the sine x. And that's when I distribute here. When I multiply it by this term, this x wipes out one of those, so I'm left with plus sine x times x to the sine x minus 1. So we get our derivative here. It's kind of interesting to notice that this was a blend of power function and exponential function, and the derivative is a blend of what you do when you have an exponential function, right? You get the base to the power times the derivative times the natural log of the base, and what you do when it's a power function, right? The power came down, you got x to 1 power less. So since this was a blend of those two kinds of functions, the answer ends up being a blend of those two kinds of procedures, partially the derivative of an exponential and partially the derivative of a power. Kind of interesting. It was pretty essential that we take the natural log of both sides so that we actually could figure out what to do in this case. Here's just another one. We, again, don't quite have a power and don't quite have an exponential. So what we can do is take the natural log of both sides, thinking to ourselves that if we do that, then this pesky square root of x and the exponent can come down, and we'll be able to deal with it a little bit easier. Now we have a product. So if I take the derivative of both sides with respect to x, the derivative of the natural log of function is the derivative of the inside over the inside. The derivative product would be the derivative of the first, which would be 1/2 x to the negative 1/2 times the second, plus the first, which is the square root of x, times the derivative of the second. The derivative of the natural log of a function is the derivative of the inside over the inside. To finish it off, we multiply both sides by y, and we get 1/2 x to the negative 1/2 times the natural log of x plus 1, plus we have here the square root of x over x plus 1, all times y, and y is x plus 1 to the square root of x. So, okay, might want to just take that and put it downstairs so that we had 1 over 2 root x times the natural log of x plus 1 plus the square root of x over x plus 1 all times x plus 1 to the root x. We could distribute like we did before as well, so distribute that term to both of these to get our answer if we liked.